Video, we're going to be covering more matrix multiplication and other operations. So we're going to go through some problems as a review on addition and multiplication. So suppose I ask you to compute the sum of a pair of matrices like this. Okay, so what does this equal? Well, we're going to add component-wise. So 1 and 1 is 2, 2 and negative 1 is 1, 2 and 3 is 5, this is 4, 8, and 1. Okay, now keep in mind that all of these matrices are 2 by 3. Their dimension is 2 by 3. Okay, so just remember, when you add matrices, the dimension of both pairs of matrices have to match up, sorry. Okay, so next, we're going to do a quick review over a scalar multiplication of a matrix. So suppose I give you a matrix like this, and I say multiply 3 by this matrix. Okay, so 3 is a number, and this is a 2 by 2 matrix. So the resulting matrix is going to be 6, 12, negative 9, and 3. Pretty straightforward. So this is scalar multiplication. Okay, so after we have a basic understanding of scalar multiplication, we can obviously do more complicated stuff. So let's do something a little more complicated. How about exercise 10.3 from the book? So we have this really big equation. Let's do it real quick. Okay, so the first thing I want to say is that when you have a minus 2 out front, you can think of that as plus negative 2 times that matrix, right? So I wrote the plus because for me that's very natural. So the idea is that you have 3 matrices, you're adding all of them, and before you add them, you first multiply the outside. So whenever I have a negative scalar on the outside, I go ahead and I add in a plus sign, assuming that I am subtracting a number, right? Okay, so when I multiply this through, I should get this. This is negative 2, positive 4, right? Negative 2 times negative 2. 6 and negative 10. And this will be 0 for negative 8, for negative 4, and negative 4. Okay, finally, I'm going to go ahead and add these 3 matrices all at once. Okay, so 6 minus 2 is 4, plus 0, so that's 4. Negative 15 plus, well, 4 and 4 is 8, so negative 15 and 8, that's going to give me negative 7. 3, 6, all right, 3 and 6 gives me 9. 9 plus negative 8, that is 1. 9 and 0 and 4 is 13. 0, 2, and negative 4, that is 2 minus 4, which is negative 2. And finally, we have 12 and 10 and 4, and they're all negative. So that's going to give us 10 and 12 is 22, and 4, that's going to give us 26, but it's negative. Okay, so that's our solution. So that's pretty much all there is that I want to say about addition and scalar multiplication. So at this point, we're going to move on to matrix multiplication. So the first thing you have to recall is that if you have a matrix A and the dimension equals, say, K and N, and B has dimension, let's say, M and P, okay? Then A times B, okay, this is going to have dimension, right? So I like to write them next to one another. So you have K and N and M and P. This is going to have dimension KP if M equals N. Otherwise, okay, otherwise it's nonsense. Okay? So all I mean by that is that you can't even do the product. Okay, so assuming the product is defined, then you take the outer pieces. Otherwise, if these do not match, it's not defined. Sometimes we also like to write, instead of, say, Kn, sometimes we like to write K times N. So, for example, a 2 by 3 matrix, we could write as 2 times 3. Okay, so for the following problems, we're going to determine the shape or the dimension of the products of a pair of matrices provided the product is defined. So suppose our first matrix has dimensions 2, 3, and the second is 3, 4. What should be the dimension of the new matrix? Well, 3 and 3, they match. So the new one should be 2, 4. Okay, so keep in mind this is matrix multiplication. Okay. Next, we have a matrix of dimension 4 by 1 and 1 by 2. So suppose you had A and B, right? So what would this look like? This would look like 4, right? 4 elements, 4 by 1, and 2 elements, right? E and F. So this would be A and this would be B. So that's what it would look like. So if I were to give you a question that had something like this, instead of A, B, C, D, E, and F, I would use some numbers. And you would look at that and you might think, oh, I can't do it. They're not the same shape. But you can do it because the inside dimensions match. Right? There's one row, there's one column here. So the new dimensions are going to be 4 by 2. And so what does that look like? Well, it looks like this. Okay? So that's what that looks like. The next question is, what is the dimension of a matrix product where the components have 1 and 2 and 3 and 1? Okay? So this is not defined, right? Not defined. Right? Because 2 does not equal 3. These don't match. if you have 5 and 2 and 2 and 3, this is going to give us 5 and 3, right? And then 4 and 4 and 3 and 3, right? This is not going to work. And if you had 2 and 2 and 2 and 4, right? These match. So you take the outside part, and that's going to be 2 and 4. Okay, it's just a coincidence that the shape of this is the shape of that, right? It doesn't have to be that way. Okay, so now that we have got some practice, we're going to do some actual matrix multiplication. So suppose A is equal to 1, 3, 2, negative 1, and B, this is going to equal 2, 0, negative 4, 3, negative 2, and 6. So there's two parts to this question. So part 1, find AB, and part 2, find BA. Okay, so again, assuming that it's even possible, right? So let's just check. So the dimension of A, this is 2 by 2, right? And the dimension of B, this is 2 by 3. So the dimension of AB, well, the inside dimensions in this case would be 2, 2, and 2, 3. And so because the 2's match, we pick the outside components and we get 2, 3. On the other hand, if I have B times A, I'm going to do this, and then I'm going to multiply this. And because the inside dimensions do not match, B times A is not defined. Okay? So it's not defined, and so the only thing that we're going to be able to actually, the only thing we're actually going to be able to compute is A times B. Okay, so let's see. Okay, not what I wanted. Okay, so you have your A. Oof. Okay, hold on 1 second. Here we go. Okay, again, not what I wanted. Okay, so we have 1, 3. Oh my gosh. Yeah. Okay, 1, 3, 2, negative 1, and 2, 0, negative 4, 3, negative 2, and 6. Okay, so we need to be able to multiply these together. So again, remember, this is 2 by 2. This is 2 by 3. And so the new matrix is going to have dimensions 2 by 3. Okay, so I'm going to keep that in mind when I draw this. So there should be 2 rows and 3 columns. So just to keep it organized, I'm going to go ahead and draw some lines in. Okay, so 1 times 2, sorry, so to get the first element in the first row, right? First row, first column, I'm going to multiply this row with this column. Okay, so I get 1 times 2 plus 3 times 3, which is 9. And then for this element, I'm going to multiply the first row and the second column. So this row, this column. So you get 1 times 0, which is 0, plus 3 times -2, which is -6. For this element, I multiply 1 and -4, so I get -4 plus 3 times 6, which is 18. And this is the 1, 3 element. Okay, so next I'm going to find the 2, 1 element. So the 2, 1 element, I pick the second row of the first matrix and the first column of the second matrix, and I'm going to multiply them. So I get 4 minus 3. Next, I want the 2, 2 element. So I pick the second row, second column, and I get 2 times 0 is 0, plus -1 times -2, which is 2. And then finally, for the last element, which is 2, 3, I'm going to pick this second row and the third column. So I get 2 times -4, which is -8, minus 6. Okay, so now that we've done one example on matrix multiplication, let's go ahead and do one more example. Okay. Right. Okay. So 1, 6, -3, 5, and 4, 0, 2, -1. Okay, so the resulting matrix is going to be a 2 by 2 matrix because, right, the dimension of each of these matrices is 2 by 2. We match the inside elements, they do match up, and so the new matrix is going to have dimensions equal to the outside, so 2 by 2. So I'm going to split this up into 4 parts, and I'm going to label these really quick. 1, 1, 1, 2, 2, 1, and 2, 2. And then we're just going to go through. So the first row and first column, right? So that's going to be 4 plus 12, okay? Then first row, second column. This is 0 minus 6. And then second row, first column. This is going to be -3 times 4, which is -12, plus 5 times 2, which is 10. And then second row, second column is -3 times 0, which is 0, plus 5 times -1, which is -5. So the solution, when you've neatened everything up, should be 16, -6, -2, -5. Okay, so sometimes when we multiply a matrix by itself, we denote that as A squared. So for example, if a matrix A is equal to 1, 2, 4, -3, sometimes instead of writing A, we just write A squared. And to compute that, you just do it as a normal matrix multiplication. Again, this makes sense because it's a 2 by 2 matrix, and a pair of 2 by 2 matrices multiplied together gives you a 2 by 2 matrix. So let's see, 1 times 1 is 1, plus 8, so that's going to give me 9. 1 and 2 is 2, so 2 minus let's see, I want to multiply this and this. So it's going to be 2 minus 6, which is negative 4. Next, I'm going to multiply 4 and 1, right? 4 and 1 and 4 and negative 3. So that's going to give me 4 minus 12. And then finally, this and this. So that's going to give me 8 plus 9. Okay, so that's going to give me 9, negative 4, negative 8, and 17. Okay, so there is something we got to be careful about, and this is the dot product versus the matrix product. Okay, so technically, a vector is a matrix. So if you have a vector, let's say 3, 1, 4, what type of matrix is this? Well, it's a 3 by 1 matrix, right? Because there's 3 rows and there's 1 column. So it's a 3 by 1 matrix. And if I do what's called the dot product, let's say we had another vector also, say 2, 1, 1. So if I take the dot product of them, I should get a number back. And the way this works is I just multiply each of the components bit by bit and add them up. So this would be 3 times 2 plus 1 times 1 plus 4 times 1. So this is going to give me 6 plus 1 plus 4, and that's 11. However, if instead of viewing this as a scalar product or a dot product, if we thought of these as a matrix product, right, then this doesn't really make sense because this is a 3 by 1 matrix and this is also a 3 by 1 matrix, and you can't multiply them together like that as matrices. Okay, so what if instead I had U and U was, let's say, 3, 1, 4. So it's just like V, but it's sideways. So this is a 1 by 3 matrix, and this is a 3 by 1 matrix, right? So if I multiply U and W, right, then the dimension is going to be 1, 3, and 3, 1. And so because those match, you get a 1 by 1 matrix. So that's a little different, right? So it's not a number like the dot product. It's actually a 1 by 1 matrix containing a single number. And so let's be careful about the way we write it. So you have 3, 1, 4, and then you have 2, 1, 1. When we multiply this together, you apply the usual matrix algebra, and you get 3 times 2 plus 1 times 1 plus 1 times 1. So you get the matrix, the 1 by 1 matrix, just consisting of the number 11. Okay? However, if you instead multiply W by U, then the dimension is going to be 3 by 1 and 1 by 3. And because the inner dimensions match, the new matrix is going to have dimension 3 by 3. Okay, so let's clean up a bit. So I had 3, 1, 4, and W was 2, 1, 1. I don't remember if that was quite it, but it doesn't matter. And I want to make that a row vector. Okay, so the point I'm trying to make here is that this is a 3 by 1 matrix, and this is a 1 by 3 matrix. So I want to multiply these together to get a 3 by 3 matrix. So V times W is a 3 by 3 matrix. And the thing is that the rules still apply. Okay? You just have to be careful, right? You just have to be careful. Okay. So the first entry is the 1, 1 entry, right? So you take the first row, which is right here, and multiply it by the first column. So that should give us 6. And now in this second element, we multiply the first row by the second column. So that's 3 times 1, which is 3. And then the first row by the third column, which is again 3. Second row by first column, 2, 1 times 2. Then 1 times 1. Then 1 times 1. Finally, the third row, and then first column, second column, third column. So this will give me 4 times 2 is 8, 4 times 1 is 4, and 4 times 1 is 4. So this is the result of V times W as a matrix. Okay, we have one last concept I would like to discuss very briefly, and this is the matrix transpose. Now, we already went over the matrix transpose, but I'll just review it here. So, suppose I have a matrix 1, 2, 0, 3, and that's a 0, 3, negative 1, 4. Then the matrix transpose, it's going to swap things around the diagonal. Now, when I previously discussed it in the last video, I used a square matrix, and that one's easier to see because you just reflect about the diagonal. But in this case, there isn't really a diagonal because it's not a square matrix. So you have to actually use the official definition, which says that the j-ith component of the transpose is just equal to the ith j component of the original. In other words, rows become columns and columns become rows. So if I transpose A, this is going to become 1, 2, 0, and 3, negative 1, 4. It's really not a difficult concept. You take the first row, and it becomes the first column. Then you take the second row, and it becomes the second column. I suppose you could say that this is a sort of diagonal because, as you can see, the diagonal remains the same. Okay, so the next thing you could do is you could multiply A by A transpose. I'm not going to do that, but I'm just saying you could do it. So let's think, what is the dimension of it? Well, the dimension of this is going to be, well, it's a 2 by 3 matrix and a 3 by 2 matrix. So if we were to compute this, the dimension would be 2 by 2. And if we were to do the computation A transpose A, then this would be a 3 times 2 matrix and a 2 times 3 matrix. And so the resulting matrix would be 3 by 3. Okay, so that's pretty much it for the basics of matrices. You know, there are some things I would like to discuss possibly next week on the determinant, but I believe that that's all we need for today, for this week. Do review these concepts, and just as a reminder, you know, the homework and the videos, they are really just the beginning of your study, right? You shouldn't contend yourself with, okay, I just did the homework. Okay, that's not enough. You need to really do these exercises until you understand the concepts. So, you know, find some examples online of matrix multiplication. Work the exercises out, and then verify that you got the solutions correct. And I can guarantee you that you will do fine on the exams. But you have to put the effort in. Okay, so email me drop me a message below on the YouTube video if you have any questions. Okay, well, good luck.